Up to this point in the class, we have pretty much always ignored the size and shape of the objects we've been studying. Think back to when we were doing Newton's laws. Whenever we drew a free body diagram, we would represent the object as a dot because it didn't matter what the object was, whether it was a baseball or an elephant or a potato or whatever it was. We would draw a dot and then we would focus on the forces that were acting on it. The size and shape didn't matter. As we move through the rest of the course, however, the size and shape of objects is going to start to matter. Our next topics involve rotational motion. And once we get into that, the size of an object matters, the shape of it matters, and it will also matter how mass is distributed inside the object. We're going to have to start taking all of this stuff into account as we think about the motion of an object, including its rotation. To take a step in that direction of accounting for the size and shape, we're going to talk here about center of mass. There's a couple of things I want to do. I want to explain to you one reason this is important. I'm going to talk about the definition of center of mass, and then I'm going to send you to a video from Flipping Physics that has a really nice summary of center of mass, and in particular it has really great animations and demos. And these are important for you to watch because it'll give you a good feel for what this center of mass is and how the motion of the center of mass compares and is different from the motion of a whole object with some distribution of mass inside it. So I'll have you go watch that in a few minutes after we talk about the definition and get an introduction to this. All right, so first, let's imagine that we have an object with size and shape. Maybe it looks like this. And we're no longer going to ignore the fact that it has size and shape. Up until now, our next step would have been to treat this thing as a particle, draw a dot, and say that the force of gravity acts right there. Any other forces on the object act on that dot. But we're not going to do that here. We're going to keep the fact that it has size and shape. Now, if I wanted to draw, for instance, the weight of this object, what I should really do is account for the size and shape by saying, okay, there's a little piece of mass right there, and that little piece of mass has a little tiny weight vector, little tiny mg, and there's a little piece of mass over here, and that little piece of mass has a little tiny weight vector, mg. And in fact, I could fill this whole object with little tiny rectangles and little tiny weight vectors. And that would be an accurate representation of the weight of this object. Imagine this area filled with little orange weight vectors. But it's terribly inconvenient for studying. What we want is some representation of the average location. It turns out that our definition of center of mass lets us say that all of the weight of this object acts at one point that we call the center of mass. I'm going to draw it right there, and let's add a coordinate system so that we can draw a center of mass vector. Go from here to here, our center of mass. That's the position of the center of mass relative to this coordinate system. And it turns out that if you add up all of the little tiny masses so that this guy has a mass capital M, and you let the whole weight of the object, capital M times G, act right there, then whether we're talking about translational motion or rotational motion, anything we do in this course, this object is going to move influenced by gravity in the same way, whether you account for gravity acting at this one point at the center of mass, or whether you account for all of the weight vectors individually throughout the object. And letting the weight act at one point, the center of mass, with the weight of the whole object, is clearly a simpler approach. So our definition of the average position of this object at the center of mass gives us the advantage of putting the weight vector at one spot rather than having to represent it being everywhere over the object. Now, what is the definition? Well, the definition of center of mass that gives us what we need is what's called the mass-weighted average position. So position of the center of mass is the sum of mi, ri, over the sum of mi. Let's talk about what this means. The numerator tells us to add up this quantity for every little chunk of the object. Here's a little chunk that maybe I would call piece 1. Here's another little chunk I could call piece 2, and I would have thousands of them filling this whole thing. This numerator says add up the mass of each individual chunk times the position of each chunk, and divide that by the sum of all the individual masses. You can see that this just equals capital M, the mass of the whole object. So we could write this as the sum of mi ri divided by the mass of the whole object. Now this is what's called the mass weighted average position. When you calculate a weighted average of something, you take that something and you weight it by whatever you want, and then you divide by the sum of the weights. In this case, what we want is the average position, and we want to weight that position by the mass at the individual locations. So our weight is the mass at each position. We multiply it by the thing we're looking for, the position, and then we divide by the sum of the weights, the sum of the masses in this case. And that's our mass-weighted average position, which we call center of mass. There are two other things we might want to do with this. We might want to write the components. The x component, how far over this way the center of mass is, xcm, is just the x component of this side. It is the sum of mi xi, add up each mass times how far along it is along the x-axis, divide by the sum of the masses, which is the total mass. And the same thing for the y component. If you want to know how far up this way the center of mass is, ycm, it is just the sum of mi yi over the sum of the masses. Okay, so that's one thing we need. The only other thing we might want to do is to see how to calculate the center of mass when we don't have what we could imagine as a collection of little rectangles or individual discrete objects, but instead we have a continuous object. Suppose I want the exact result. I don't want to calculate the center of mass of maybe 10 or 20 of these little things. I want to imagine that I let this thing become infinitely small. What happens in that case is that these summations turn into integrals, and you can calculate RCM this way. It becomes the integral of R dm over the integral of dm. So you could write this as R dm over the total mass of the object. So when you have a continuous object, not a collection of individual ones, you would use this expression. All right, I'll ask that you go watch the video from Flipping Physics on center of mass. There's good illustrations and demos there. And then after that, we'll do some examples and problems on this topic. So we'll see you back here when you're done watching that.